Hello everyone, this is Jean-Paul Jung. I will explain Introduction to Data Structures. Today's topic is Insertion Sort and Merge Sort. The reference book is Introduction to Algorithms, written by T. Coleman, C. Laser, Son, R. Levesque, and C. Stein from MIT Press. Okay, so you can refer to this textbook. So insertion sort, input is A1, A2, AN. We can assuming this is positive integers, okay? Or you can see some poker cards, okay? So poker cards shape and number, okay? According to shape, clover, spade, heart, something like that, right? And the number is a high number is a high value. So and then output is A1 prime, A2 prime, blah blah blah, A and prime is such that this is non-decreasing order, right? So which means the first one is the smallest one and the second one is equal or greater. So this is called a non-decreasing order. So algorithm sketch, the gray one is sorted, white is a new item, green is okay, unsorted. So first that we have a point. So first one is already okay, we can send okay, sorted. And then the idea is we have some card and then we can try to the previous deck of cards already sorted, and then we can scan from rightmost toward the leftmost, right? And then if my card value is greater or equal to my current compared card, I just insert, okay? If my value is less than current okay, P point, right, compared card, I have to move to the left, okay, until I find appropriate position. So compare, okay, this one is value is greater than or equal to case, done. Okay, you're done. And then third one is compared, okay, new item, and then compare something. And then we can, one step at a time, we can appropriately find some position, something like that. And then we can finish, okay, insertion, something, we are done. So, okay, working item here. Okay, first one is, we assume this already sorted, okay. And then second one, we compare 5 and 2. So this is less. In that case, we can swap. Okay, swap. And then this one, right? So in that case, swap means that we insert this in front of this one. In that swap. The step 2 case, this one, 4 and 5. So 4, right? So in that case, we can move to left, right? So swap something. Okay. And then 6 is already greater than this. Okay, we are done. And then 1 is okay, less than this one, less than this one, and then this one going to the first index item, right? Something like that. And 3 case, we can see okay, 6 okay, greater, so move to left. And then 5 is greater than this, left. 4 greater than this, and then okay, and then 2, this one, right? So and then 3 going to this index 3, something like that. We are done. So the pseudocode of insertion and sort, okay. So the first item is we assume already sorted, right? And then the goal is we find the appropriate position for this new item. So J is start from index 2 to A length. Remember this pseudocode case, first item is index is 1 rather than 0. This is like different from C over C++, okay. And then the key is A is input array, right? J, the second okay item. So we want to find a J into a sorted okay arranged part, gray part, okay. First one up to J minus, right? Because J is current my card or my value to insert this range. And then J minus, the I is actual searching index, right? So J minus 1 is I need to check, right? First. So I is as long as positive, okay, and then I is a key. Key is we want to insert, right? So this is a greater case. So this key value is less, right? So we can search it to the left, right? And then we can swap, okay? I value I plus 1, right? So we swap, okay? Because this is a searched one. I plus 1 is current my key value is position, right? And then I is decreased by 1, and then we can keep going. And then if we cannot satisfy this one, exit. I plus 1 is the position I want to insert, okay? So such as I is okay, compare the one, right? So compare one such. So in that case, I plus 1 is the appropriate position because I is not okay less than this key value, right? Or so in that case, we can okay check I plus 1 is the appropriate value. So if the key and the same case also we can as long as the same case we don't need the right change, right? Swap. So in that case I plus 1 is the place for key value. So loop invariant is the property okay in the loop. So definition of a loop invariant is the property of a data structure that is always true within a loop, like a for loop or a while loop. Loop invariant in the insert sort A case. A is input array. The subarray 1 blah blah j minus 1 is already sorted on, right? Consists of the elements originally in the A1 j minus 1, but in sorted order, okay? The purpose of a loop invariant case to show that an algorithm is correct, okay? So once we sorted a whole input A, and then we the property is sorted order, right? Non-decreasing order. In that case, we are done. We terminate the algorithm, and our goal is sorting the items in non-decreasing order, like the ascending order. 3 things for loop invariant. So we have 3 the steps. The first step is initialization. It is true prior to the first iteration of the loop, okay, before the looping, and maintenance case after iteration. If it is true before an iteration of the loop, it remains true before the next iteration, okay? So the property is maintained. And the termination case, the step 3, when the loop terminates, the invariant gives us a property to show the algorithm is correct. Like we are done the input and all input range are non-decreasing order. So in that case, our goal is done, right? So algorithm is proved to be correct. So loop invariant in insert sort, right? Initialization A1. This is the first one case already sorted when J is 2, right? So we start J2, right? Because the first one is already sorted. The maintenance case before and after the loop iteration A1 up to J1 consists of the elements originally in A1 up to J minus 1 before AJ is inserted appropriately, okay, to appropriate position, but in sorted order. After that loop iteration, we find the appropriate position we insert, right? So A1 up to J consists of the elements originally in A1 up to J. After AJ is inserted appropriately, but in sorted order, the ordering the property is preserved. Termination, step 3. For the termination condition, J, this is greater than the input array length. The entire array A1 1 up to n is sorted. Okay, so analyzing time complexity for insert and sort, right? So this is you can see C, and this we can say this state the line 1 cost is C1. The iteration is you can see, okay, first, okay, 2 up to length, okay, and then the next, the J becomes length plus 1 case, it actually, right? So actual times the comparison, this one is n times, and key value is actually this iteration is length, we can say n, length is the number of input size, we can say n case, actual iteration lines 2 up to 7 is n minus 1, and this line is C2. Okay, comment case, the actual cost is 0 because compiler is get rid of this comment from source code, right? And then n minus 1. This assignment is, we can say C4 n minus 1, and this one is a little tricky. So we can say this while this statement C5, and then this performed. Okay, so J2 up to n, okay, up to n, TJK depending on actual the scanning from rightmost leftmost, right? So in that case, at most, okay, J, okay, J is you can see 2, right? From 2 and this is n, right? And then this actual comparison depending on the situation, we can say that iteration is a TJ case, this one. Okay, also last one also compare to exit the while loop, that's why we have this TJ. Okay, otherwise TJ minus 1 because this is iteration line 6 or 7 is actual this comparison case, this is one more than this one. Okay, and then we can have these summations. Finally, we copy key value to appropriate array A I plus 1 case, the cost is C8. Okay, so this is n minus 1 because this is within a for, right? So learning time, we get the sum up, right? C1 times n, C2 n minus 1, something like that. We have this one. Okay, so the time complex, the best case learning time, the best case if array is already sorted case, you can see just compare just to the left, just adjacent to the left one company is enough, right? If the sorted case always the checked one is greater than or equal to left neighbor, right? So that case company is CJ, TJ is small, just one comparison. Okay, so in that case you can see this is a C5 is 1. Okay, and then also just this is we can say 1, and then 2, 3, 4, 5 is actually the iteration is almost n, right? So that's got n. Okay, so other case you can see just C1 this term, and this one is C5, C6, C7 case we consider. Okay, this one, right? So this is n minus 1 C5. Okay, this one is okay, from 2 n is the number is n minus 1, and this one is n minus 1, this is n minus 1, right? N minus 1, n minus 1. Okay, so we we rearrange. Okay, eventually it's constant, this is constant minus, right? So this is n. Okay, n. So worst case, we if the array is reversed sorted case, worst, right? So in that case, this summation is worst case summation value, and then we can arrange we have n square. Okay, so this is n square is worst case time complexity. So worst case for time complexity, the worst case learning time of an algorithm gives us an upper bound on the learning time for any input. For some algorithms, the worst case occurs fairly often. For example, search for absent information in database. 3. The average case is often roughly as bad as the worst case. Okay, so usually we consider worst case time complexity, but quicksort we are learn later on. We focus on average case, but quicksort is actually the fast algorithm. Okay, so designing algorithms. So we have two approaches. One is incremental approach. The second one is divide and conquer approach. Okay, insert sort is incremental approach. Okay, divide conquer case merge sort we will see. This is the divide conquer approach. For sorting, divide and conquer approach, merge sort and quick sort has much less worst case learning time than incremental or linear approach like insert sort. So divide and conquer approach consists of 3 steps: divide, conquer, merge. So let's take a look at famous divide and conquer approach merge sort. So we have this unsorted sequence in divide sequence. We can divide one half and the other half, and also divide one half divided, one half divide another half, until each one has one element. Okay, so this is the divide phase. The merge case, we can adjacent the two smallest bucket. This one merge. Okay, like, and 2 and 5 compare. This one is compare merge. This one compare. Well, last one is left, greater than is right. So we merge like this. Also, next level we also merge this one, right? This one compared. Okay, 2 is less than this one, right? So this copy first, and then we compare 5 and 4. Right? 4 is this one, and the 5 7, and the 5, and the last one is 7. Similarly, 1 3 2 6 is we merge like this. Okay. And then finally, this 4 bucket, and 8 bucket is used to merge. Okay, first one, we use 2 index as a pointer, 2 and 1 compare, 1 and then go, and then to the moved, and then 4 and 2 compared. Okay, something. So and 2 move, and then 3 is less than 4, and the 3 copy, and after that 4 and 5 6 compare. 5 is a small, this one, and then 6, and then last 7 going to this merge. Okay, so merge sort algorithm so consists of divide and merge. Okay, so merge sort case input array is A and P is the index left, and the right is right, and then Q is the middle point, the divide, we can division index. Okay, and then P and the middle point Q, and the middle point Q plus 1. Okay, this is adjacent for middle point Q, right? And then R right, bound. So divide and conquer something, and then we can merge, right? So this one is done. So this recursively call, right? So this call and this one repeat. So this call is eventually like call divide. Okay, so this is divide and then conquer after the merge. Okay, so divide and then conquer. Okay, something like that, and then after this left half, right half, they are merged. This is called the merge. Okay, so merge case, the n1 n2. Okay, the number is q minus p plus 1. This is the number, the range. Okay, so this one is less than, because the index is you can see the q plus 1, right? So this case q minus p plus 1. Okay, this one, and this is r minus q. Okay, because the r q plus 1 plus 1, this is actually the number. The first half, there's a second half. The original one is split first half, the split right half, right? So the index point of view 1 up to n1 plus 1. This is 1 n2 plus 1. Okay, this one is a kind of the marker for end one, okay, in the bucket new array. And then the line 4 and 5, and then we can merge, right? We can okay, copy this one, p plus I minus 1, and then we can just copy this one. So this is merging array. This one also copy from q plus j, okay. This one q plus 1 up to this n plus 2, right? So this copy, and then this is a marker, okay, infinite value, and then I and j is a pointer index, okay. So and the compare, right? So the r l I r j start k, okay, is actually merged, okay, bucket index, right? P and R, and then we can using this, okay, the temporary bucket left hand side, right hand side, and then this is less than or equal case. This one is appropriate value, right? We copy here, increase I, so the left bucket index move to right, and then otherwise the right bucket j index is copy, okay, here j plus 1, okay. So and then we can okay, and the other case we just copy and then increase the j index. So invariant emerge, step 1, at the beginning of the, okay, for loop of lines 12 through 17, a p, okay, up to k minus 1 contains, okay, k, okay, so k plus minus 1 minus p plus 1, right? So in the kp, smallest element of this one and this one, okay. And then li rj are the smallest element. They are arrays that have not been copied back into A, right? So this one is the invariant, okay. So the 12, this one 7 we reserve, we can copy and then we can see so this p k minus 1, right, pk, and then p and k minus 1, so that is contains this kind of number, okay. And then we can copy remaining element in the L buffer, remaining element R buffer, and then compare and then move I and j index like this, okay. So I and j index we can compare. So second one is Li, Lj are the smallest elements of the arrays that have not been copied back into A, right? So I and j increases, okay, until all elements in L array and R array they merged. Analyzing and divide and conquer, time complexed by recurrence, okay, recursive function call. So if n is okay less than or equal to c, okay, certain less than some threshold, this one is just constant, okay, function cost zeta 1. Otherwise we divide, okay. So subproblem n parameter divide n over b, we divide the by b, okay. And also the subproblem, this, okay, cost is a, okay, times, and then other cost is this is divide and this conquer, okay, a kind of divide and conquer, okay. So divide actually this is conquer, okay, cost. So something this is combine merge cost, okay. So this is n over b t case time to solve one subproblem of size n over b. Input size becomes n over b, okay. Original size n divided by b. This is actually, okay, divide conquer problem, subproblem, okay. We can say conquer, and dn case divide the original problem into sub problems, right? So divide division cost. cn is merge cost. Combine the solutions to sub problems into the original problem. So time complexity of a merge sort case, okay, if the element becomes one element case, the time complexity is just a constant 1. Otherwise, we divide the input bucket into 2, right? Divide, okay? So divide and conquer, right? This cost, this is 2 times t n over 2. And this shatter is actual divide, index. Okay, find the middle point, current input, and the merge cost, okay? This is n is greater than 1. So divide, compute the middle of the sub array, okay? So this is okay, finding divide, okay, approach, right? This one is just start index and then last index sum divided by 2 is the okay midpoint. Conquer case 2 sub problem to solve. Each size n over 2, 2 times t n over 2. This is a sub problem. Input size reduced by this one factor and times, because 2 sub problems, okay, divide from original problem. And combine, this is merge. So merge on n element sub array takes zeta n, okay? So that's why, because we can scanning, right? So the actual scanning number is n. So zeta is n. So we can say zeta case the polynomial point is the order is 1 and times coefficient constant number c. So recursion tree, let's take a look tn and 2tn n over 2 and cn, right? This is divide and the merge combine cost. This is conquer, okay? So cn input and we divide like this, and also we divide the 2 problems, something like that, okay? Or sum is a cn, this is sum is cn, but the number of depths is log n, okay? So we can divide, and so we can calculate the depths k, okay? So because you know cn and divide 2, and then the exponent k equal this 1 case, we can find the k value, okay? So that's height is log n. So total is log n plus 1 cn, okay? Because this length is height is log n case, log height, and plus 1 is actual the number of levels, and each okay level cost the cn times, okay? So eventually n log n is merge sort, okay? Time complexity. Insertion sort is n square. Merge sort is you can see this in terms of zeta log n times n, right? N log n. So insertion sort time complexity is higher than merge sort, okay? So merge sort has less time complex than insertion sort, which means is quicker than okay insertion sort. Thus, divide and conquer approach is better than incremental approach, okay? So thank you for your attention. If you have a question, please let me know. Thank you.